In mathematics and computing, universal hashing refers to selecting a hash function at random from a family of hash functions with a certain mathematical property. This guarantees a low number of collisions in expectation, even if the data is chosen by an adversary. Many universal families are known, and their evaluation is often very efficient. Universal hashing has numerous uses in computer science, for example in implementations of hash tables, randomized algorithms, and cryptography. Introduction. Assume we want to map keys from some universe into bins. The algorithm will have to handle some data set of keys, which is not known in advance. Usually, the goal of hashing is to obtain a low number of collisions. A deterministic hash function cannot offer any guarantee in an adversarial setting if the size of is greater than, since the adversary may choose to be precisely the preimage of a bin. This means that all data keys land in the same bin, making hashing useless. Furthermore, a deterministic hash function does not allow for rehashing. Sometimes the input data turns out to be bad for the hash function, so one would like to change the hash function. The solution to these problems is to pick a function randomly from a family of hash functions. A family of functions is called a universal family if, in other words, any two keys of the universe collide with probability at most when the hash function is drawn randomly from. This is exactly the probability of collision we would expect if the hash function assigned truly random hash codes to every key. Sometimes, the definition is relaxed to allow collision probability. This concept was introduced by Carter and Wegman in 1977, and has found numerous applications in computer science. If we have an upper bound of on the collision probability, we say that we have almost universality. Many, but not all, universal families have the following stronger uniform difference property. When is drawn randomly from the family, the difference is uniformly distributed in. Note that the definition of universality is only concerned with whether, which counts collisions. The uniform difference property is stronger. An even stronger condition is pairwise independence. We have this property when we have the probability that will hash to any pair of hash values as if they were perfectly random. Pairwise independence is sometimes called strong universality. Another property is uniformity. We say that a family is uniform if all hash values are equally likely. For any hash value, universality does not imply uniformity. However, strong universality does imply uniformity. Given a family with the uniform distance property, one can produce a pairwise independent or strongly universal hash family by adding a uniformly distributed random constant with values into the hash functions. Since a shift by a constant is sometimes irrelevant in applications, a careful distinction between the uniform distance property and pairwise independent is sometimes not made. For some applications, it is important for the least significant bits of the hash values to be also universal. When a family is strongly universal, this is guaranteed. If is a strongly universal family with then the family made of the functions for all is also strongly universal for. Unfortunately, the same is not true of universal families. For example, the family made of the identity function is clearly universal, but the family made of the function fails to be universal. UMAC and Poly 1305, AES and several other message authentication code algorithms are based on universal hashing. In such applications, the software chooses a new hash function for every message, based on a unique nonce for that message. Several hash table implementations are based on universal hashing. In such applications, typically the software chooses a new hash function only after it notices that too many keys have collided. Until then, the same hash function continues to be used over and over. Mathematical guarantees. For any fixed set of keys, using a universal family guarantees the following properties. For any fixed in, the expected number of keys in the bin is When implementing hash tables by chaining, this number is proportional to the expected running time of an operation involving the key, the expected number of pairs of keys in with that collide. The total number of keys in overflowing bins is at most. This only holds with the hash family whose collision probability is bounded above by. If a weaker definition is used, bounding it by, this result is no longer true. As the above guarantees hold for any fixed set, they hold if the data set is chosen by an adversary. However, the adversary has to make this choice before the algorithm's random choice of a hash function. If the adversary can observe the random choice of the algorithm, randomness serves no purpose, and the situation is the same as deterministic hashing. The second and third guarantee are typically used in conjunction with rehashing. For instance, a randomized algorithm may be prepared to handle some number of collisions. If it observes too many collisions, it chooses another random from the family and repeats. Universality guarantees that the number of repetitions is a geometric random variable. Constructions. Since any computer data can be represented as one or more machine words, one generally needs hash functions for three types of domains: machine words, fixed-length vectors of machine words, and variable-length vectors. Hashing integers. This section refers to the case of hashing integers that fit in machines' words, thus, operations like multiplication, addition, division, etc. are cheap machine-level instructions. Let the universe to be hashed B. The original proposal of Carter and Wegman was to pick a prime and define where a randomly chosen integer's modulo with. To see that as a universal family, note that only holds when for some integer between in. If the difference is non-zero and has an inverse modulo. Solving for yields. There are possible choices for and varying in the allowed range, possible non-zero values for the right-hand side. Thus the collision probability is. Another way to see is a universal family is via the notion of statistical distance. Write the differences. Since is non-zero and is uniformly distributed in, it follows that modulo is also uniformly distributed in. The distribution of is thus almost uniform, up to a difference in probability of between the samples. As a result, the statistical distance to a uniform family is, which becomes negligible when the family of simpler hash functions is only approximately universal for all. Moreover, this analysis is nearly tight. Carter and Wegman show that whenever avoiding modular arithmetic, the state-of-the-art for hashing integers is the multiply-shift scheme described by Dietz-Felbinger et al. in 1997. By avoiding modular arithmetic, this method is much easier to implement and also runs significantly faster in practice. The scheme assumes the number of bins is a power of 2. Let B the number of bits in a machine word. Then the hash functions are parametrized over odd positive integers. To evaluate, multiply by modulo and then keep the high-order bits as the hash code. In mathematical notation, this is and it can be implemented in C-like programming languages by greater than. This scheme does not satisfy the uniform difference property and is only almost universal for any. To understand the behavior of the hash function, notice that if and have the same highest order m bits, then has either all 1s or all 0s as its highest order m bits greater than where is a random odd positive integer with an is a random non-negative integer with these choices of an for all. This differs slightly but importantly from the mistranslation in the English paper, Hashing Vectors. This section is concerned with hashing a fixed-length vector of machine words. Interpret the input as a vector of machine words. If is a universal family with the uniform difference property, the following family also has the uniform difference property, where each is chosen independently at random. If is a power of 2, one may replace summation by exclusive or, in practice, if double precision arithmetic is available, this is instantiated with the multiply-shift hash family of. Initialize the hash function with a vector of random odd integers on bits each. Then if the number of bins is 4, it is possible to halve the number of multiplications, which roughly translates to a twofold speed up in practice. Initialize the hash function with a vector of random odd integers on bits each. The following hash family is universal. If double precision operations are not available, one can interpret the input as a vector of half words. The algorithm will then use multiplications, where was the number of half words in the vector. Thus, the algorithm runs at a rate of 1 multiplication per word of input. The same scheme can also be used for hashing integers, by interpreting their bits as vectors of bytes. In this variant, the vector technique is known as tabulation hashing, and it provides a practical alternative to multiplication-based universal hashing schemes. Strong universality at high speed is also possible. Initialize the hash function with a vector of random integers on bits. Compute. The result is strongly universal on bits. Experimentally, it was found to run at 0.2 CPU cycle per byte on recent Intel processors for hashing strings. This refers to hashing a variable-sized vector of machine words. If the length of the string can be bounded by a small number, it is best to use the vector solution from above. The space required is the maximal length of the string, but the time to evaluate is just the length of, as long as zeros are forbidden in the string. The zero padding can be ignored when evaluating the hash function without affecting universality. Note that if zeros are allowed in the string, then it might be best to append a fictitious non-zero character to all strings prior to padding. This will ensure that universality is not affected. Now assume we want a hash where a good bound on is not known a priori. A universal family proposed by treats the string as the coefficients of a polynomial modulo a large prime. If let be a prime and define, where is uniformly random and is chosen randomly from a universal family mapping integer domain. Using properties of modular arithmetic, above can be computed without producing large numbers for large strings as follows. uint hash uint h equals initial underscore value for h equals plus x I mod p return h. Above algorithm is also known as multiplicative hash function. In practice, the mod operator and the parameter p can be avoided altogether by simply allowing integer to overflow, because it is equivalent to mod in many programming languages. Below table shows values chosen to initialize h and a for some of the popular implementations. Consider two strings and let be length of the longer one. For the analysis, the shorter string is conceptually padded with zeros up to length. A collision before applying implies that is a root of the polynomial with coefficients. This polynomial has at most roots modulo, so the collision probability is at most. The probability of collision through the random brings the total collision probability to. Thus, if the prime is sufficiently large compared to the length of strings hashed, the family is very close to universal. Avoiding modular arithmetic. To mitigate the computational penalty of modular arithmetic, two tricks are used in practice. One chooses the prime to be close to a power of 2, such as a Mersenne prime. This allows arithmetic modulo to be implemented without division. For instance, on modern architectures one can work with while s are 32-bit values. One can apply vector hashing to blocks. For instance, one applies vector hashing to each 16-word block of the string, and applies string hashing to the results. Since the slower string hashing is applied on a substantially smaller vector, this will essentially be as fast as vector hashing. One chooses a power of 2 as the divisor, allowing arithmetic modulo to be implemented without division. The NH hash function family takes this approach.